Hello everyone. In this video we are going to talk about only series with positive terms and some conditions to tell when they converge or diverge. So first on the docket is the integral test. So again, this is only going to work for series with positive terms. So in this case, we're going to have the summands be an, and we will have a of x describe the function such that when you plug in integer points, you get exactly the terms of this sequence. If a of x is a continuous, positive, and decreasing function on the interval from 1 to infinity, then basically what we're saying is the series and the improper integral here will do the same thing in terms of convergence or divergence. If one converges, the other does. If one diverges, the other one does as well. So why do we have these conditions? So continuous basically ensures that the integral will work out. And then positive and decreasing is what is going to allow us to compare these things nicely. So let's get some intuition as to why this actually works. All right, so why does the integral test work? So we're going to look at two pictures to justify this. So remember, we want a positive, so we're above the x-axis, decreasing continuous function. So think something like this. And we're actually going to go back to Riemann sums. So first we're going to do a left sum. Okay, and this will start at 1, go 2, and so on. Okay, so why is this useful? Well, our Riemann sum is going to be exactly what? So if we make all of these length 1, then our Riemann sum is exactly our series, right? Because we had a of 1 is a1, a of 2 is a2, and so on. And so our Riemann sum is exactly a1 plus a2 plus a3 because our widths are all 1. And so we get exactly our series. So why is this nice? Well, we know how this compares to the integral, right? This is clearly an overestimate. We're filling in this stuff above. And so we can say that our series is greater than the integral from 1 to infinity of a of x dx. Okay? So this is one way, and here we can kind of use comparison, right, to say that if, for instance, the series converges, then the integral is going to converge as well. So then we have to worry about, okay, what if the series diverges? How do we know that the integral is going to diverge? So to do this, we're going to draw another picture, and we did the left sum up above. We're going to do the right sum down below. So got 1, 2, 3, and so on. So here we're going to do the right sum. So by the same logic, here we see an underestimate, right? We're missing these little gaps in here. But we start at a of 2, which is a2. So we're really looking at the series n equals 2 to infinity of an, and this is less than the integral from 1 to infinity of a of x dx. So you might say, okay, well, this isn't exactly what we wanted, but we can then say that our series is less than a1, just adding a1 to each side, a1 plus the integral of ax dx. So if our series diverges, then what's going to happen? Well, we have something that's greater. So we have that a1 plus our integral diverges because it's greater. And hence, since a1 is just some finite number, right, that's not going to change this going off to infinity. So this means that the integral itself must have diverged. Okay, so now we know if the series converges, the integral converges, and if the series diverges, the integral diverges. And this is exactly what we wanted to show. All right, so let's use the integral test to show this fact. So this is what's called the p-series test. And more generally, we can actually say that the series of the form 1 over an plus b to the p converges if and only if p is greater than 1, where a and b are just real numbers. So essentially, you don't just have to deal with an n to the p, but you can actually have a linear term on the inside. And the argument is pretty similar. So we're just going to show the easier case, and if you feel super motivated, you can actually prove the other one on your own. So now to apply the integral test, we need those three things to be satisfied, right? So this 1 over x to the p, right, because we're going to want the continuous one. So first of all, this is continuous on the interval from 1 to infinity. Yep, we're not getting 0 in the denominator. It is decreasing, right, because we have x getting bigger and bigger, and thus the fraction itself getting smaller and smaller, and all of the terms are positive, right? Again, we're on 1 to infinity, so we're taking powers of positive numbers. So we hit all three of the things, so the integral test applies. And thus, to look at convergence or divergence of the series, it suffices to look at the improper integral 1 over x to the p dx. Well, we already know what happens with this one, right? So you can even do it out. So we have this, we're just rewriting the improper integral. So if p is not equal to 1, then this is just reverse power rule, right? And so we'll just add 1 to the power, and we need to divide by that power, so we get this. And once you plug things in, right, then the one term basically is not going to end up mattering. You just get minus 1 over 1 minus p. It's really when you plug in b that you get something interesting. So we get b to the 1 minus p here. And so with b going off to infinity, it's really, okay, something going off to infinity to the 1 minus p power. When is this going to go off to infinity itself? And when is this going to go to 0? And that's going to depend on your value of p, right? So p greater than 1, then it's a negative power, right? So you have 1 minus p then is less than 0, and thus b to the 1 minus p is going to go to 0 because you basically have an infinity in the denominator. On the other hand, if p is less than 1, 1 minus p is greater than 0, and you're taking a base that gets really large to positive powers, and thus b to the 1 minus p goes to infinity. And so if p is less than 1, we get it diverges. If p is greater than 1, it converges. What happens if p equals 1? Well, that's the case where we have just the integral from 1 to b of 1 over x dx, right? So this is where we have the natural log. And so the natural log of x from 1 to b, well, we're just going to get ln of b minus ln of 1, which is 0. Take the limit, and that's going to be infinity all the time. And so it also diverges if p equals 1. And so this is exactly what we wanted to show, right? So it converges if p is greater than 1, and it diverges otherwise. All right, and so for your first exercise, I want you to use the integral test to determine if this series converges or diverges. And I'll just make the note that the fact that it starts at n equals 2 here isn't really going to change anything, except for you do want to look at the integral from 2 to infinity and not 1 to infinity. Why do we have 2 here and not 1? Well, what is the natural log of 1? It's going to be 0, right? So we want to avoid that asymptote, and so we're going to start a little bit to the right of it. So next on tap is the direct comparison test. So again, we want sequences with only positive terms. And here we're going to suppose that your an terms are eventually less than your bn terms, or less than or equal to, right? So that's what this n is greater than or equal to capital N thing is saying. Basically, once you're past this threshold capital N, your an terms are always no bigger than your bn terms. And so the result is exactly what you would expect, right? So from the improper integrals. So if the series of the bn converges, well, this is the bigger one. And so then the smaller one must also converge and go to a finite number. If the smaller one goes off to infinity, then the bigger one has to be bigger and must diverge as well. Okay. And this is where it's important that the series have positive terms, right? Because diverging with only positive terms is going to ensure that you actually go off to infinity. And also you want it for the case where the bigger ones converge, because being smaller than something that converges, if you, for instance, just your terms go off to negative infinity, then you're always less, but then you would diverge. So it's important that you're bounded below by 0 there. So for an example, let's look at this one here. So we've got 1 over the square root of n times 3 to the n. And the reason this is nice to consider is we have kind of two things that seem reasonable to compare to, right? So it seems like we could compare to 1 over root n, or we could compare to 1 over 3 to the n. So which one is better? Well, what's actually true? So 1 over root n times 3 to the n, well, having these other terms in the denominator that are always bigger than 1, once you're past a certain point, means that this is simultaneously less than 1 over root n and less than 1 over 3 to the n. Now, we know that this guy, the series of 1 over root n, diverges, right? Because this is with p equals 1/2, which is less than 1. On the other hand, this guy converges. Why? Well, it's secretly 1/3 to the n, which is geometric, and our ratio is less than 1, so it's going to converge. So which one should we compare to? It seems like we're seeing different things, but again, being less than something that diverges is just inconclusive. So we want to compare to this one because we're less than something that converges, and thus this must also converge. So now the next one we're going to look at, and final one we're going to look at, is going to be when these inequalities don't quite match up the way we want them to, but we feel like we have the right answer. So let's look at an example to see what I'm talking about. So let's consider this series here. So the most natural comparison, right, would be to the series of 1 over n squared, because they look an awful lot alike, right? We're really considering just kind of the highest power. This -1 really shouldn't make much of a difference, right? And of course, by the p-series test, we're going to be able to say that this guy converges, right? Your p is 2 and is greater than 1. But which way does our inequality go? So we have 1 over n squared minus 1 is actually greater than 1 over n squared, right? Because we're taking away from the denominator. Well, that's a problem, because greater than something that converges is inconclusive. So direct comparison is actually not useful here. It's inconclusive. But it seems like this should be the right comparison, right? Like 1 over n squared versus 1 over n squared minus 1. These should do the same thing, right? This should converge. So this is where we actually have what's called the limit comparison test. Okay, so for the limit comparison test, we again want all positive terms, and we're going to let L be the ratio of the an term over the bn term. We're going to take this limit to infinity. Okay, so we're going to have 3 cases. So first, if this L is some positive number, okay, so finite number, then our series do the same thing. So the sum of the an's converges if and only if the sum of the bn converges. So why is this true? Well, again, this is like a ratio, right? So you can't just directly multiply over, but the idea is that basically your an is approximately L times your bn. And so you could just pull the L out of all of these terms, right? And so an, that series, is going to be L times the bn series. And so if one is finite, the other is going to be finite. It's just a multiple of the other. So this is the idea. Okay, what if L is infinity, right? What if the limit goes off to infinity? Well, what's that really saying? This just says the an are way bigger than your bn, right? That's what it means for this fraction to go off to infinity. So what does this tell us? So we have one that's way bigger. We can use direct comparison then, right? So we know the an are bigger and thus the bn are smaller. So here, if the an, the sum of the an's, converges, then the smaller guy must also converge by direct comparison. And then the last one is the same idea, but the other way around, right? So If L is 0, then what does this mean? Our Bn are bigger. And so in this case, we can again use direct comparison and say, hey, if the sum of the Bn converges, then the smaller guys, the An, this series must also converge. So basically, if your L is a finite number, they're going to do the same thing. If L is infinity or 0, you can only get an implication one way. So now let's apply it to that example up above, right? So here, if you have your An is 1 over n squared minus 1 and your Bn is 1 over n squared, then your L is going to be the limit of 1 over n squared minus 1 over 1 over n squared. Well, you can just multiply up, and we look at n squared over n squared minus 1. As n goes to infinity, this is just going to approach 1. And so this is in the first case, and so we know that the series of 1 over n squared converges. Why? Well, that's just by the p-series test, right? And so once we know that one converges, this implies that the 1 over n squared minus 1 series also converges. All right, and for your second exercise, I want you to go ahead and use the limit comparison test to determine the convergence of this series. All right, thank you for watching.